Hello students, in this session we will begin using GROMACS to perform molecular dynamic simulations. And because this is a rather complicated process, I'll begin with the simplest possible molecular system, which is a single protein molecule in solution. In the upcoming sessions, we will move on to the more complex systems, and I'll provide more details about MD simulation. But for now, you learn the overall steps of an MD simulation, and I will introduce you to the various GROMACS input and output files. Alright, first we need the protein molecule, and a good source of them is the RCSB PDB website. Here you can search and download protein structures, and every protein has a unique ID, and I'm gonna search 1UN3, this protein. I have chosen this protein because this is quite a small one and the simulation will be very fast. Alright, let's see what we have here in this page. First of all, you should know that this is an experimental structure, which means someone somewhere did the experimental analysis to detect this protein. In this case, the method was X-ray diffraction and the resolution was 1.7 angstrom. You can find other useful information about this protein like mutations, express system, and organism, the source of the protein. This is a Homo sapiens protein, which is a species, and classification, this is a hydrolyzed protein. And also this is a link to the original paper that reports the detection of the protein. Just click on it, and here this is a DOI for the PDB and also a DOI for the publication. Alright, another piece of information which is important for simulation is the protein atom count. The higher the protein atom count, the more computational power required. Alright, let's download the structure from here, and I'm gonna choose PDB format. Now I have the structure on my system. To begin the job, I'm going to create a new folder on my desktop. Let's name it session 2, and I'm going to copy the PDB file to this new folder. And enter the folder by cd command. Okay, a PDB file is a text file that contains the geometric information of atoms. You can open it using any text editor like Nano or VI. The main part of the file is the atom and het atom records. In a PDB file, each line is a record and each column can contain a specific type of data. For example, in an atom record, column 1 to 4 is the record type, column 7 to 11 is the atom serial number, columns 13 to 16 is the atom name, actually the atom type name, columns 18 to 20 is residue name. I'll tell you what's the residue later on. This is the chain identifier in column 22, and this is the residue sequence number. These columns 31 to 54 are the Cartesian coordinate of the atom and some more information. For GROMACS, the atom number, the atom name, the residue name, chain identifier, the residue number, and the atom Cartesian coordinate are important. So GROMACS won't read every data in PDB files. However, I'd recommend reading this page which explains the PDB file format. Especially you must learn the atom record type. I'll put the link in the descriptions. Okay, this file contains a protein structure data, and we can check the structure using a Visualise software. I've already taught you how to install VMD on Linux, so we can use it, and the name of the file. Alright, this is the protein structure, and you can change the visualization style from here. This is the line style. You can change it to CPK, VMD, and other visualization method. Okay, let's put it on lines. As you can see, there are some red dots around the protein structure. The red dots are oxygen atoms. Actually, they are water molecules that have been detected by the X-ray machine. And because X-ray analysis can't detect hydrogens, they are only oxygens. So first thing first, we need to remove these remaining of water molecules, and later on we will add a water model to the system. And actually, this is a really easy job in Linux. If I check the PDB file again, you can see that the residue name of oxygen atoms, actually the water oxygen atoms, are HOH. So we need to remove every line containing HOH. To do so, we can use the grep command by grep VHOH and the name of the file. The option V means I want the command to exclude all the lines with HOH in them and print all other lines. And this is the result. However, I want them in a new file, so let's modify the command to the 1un3 no water.pdb. Now I have the protein structure without the remaining of water molecules. Let's check it with VMD. Okay, as you can see, now there are no red dot in the structure. And next step, we must create the GROMACS input files. But before we begin, just a quick note about GROMACS input files. A GROMACS simulation requires at least 3 input files. A coordinate file containing the molecular structure. It can be in the protein data bank format or in the GROMACS native GRO file. And it also needs a topology file. A topology file has the top extension and specifies how different atom types of systems interact with each other. Do you remember the concept of the force field from the previous session? A topology file contains information about a force field related to the understudied structures. And GROMACS creates topology files from data of the chosen force field. Some simulations may also need ITP files because a main topology file sometimes needs some subtopology files to work. And we specify these subtopology files with an ITP extension. I'll show you ITP files in the following sessions, and a simulation also needs an MDP file. This file contains the simulation's parameters and dictates how it must be performed. Okay, these 3 files are necessary for every simulation, but some simulations also need some additional input files, like an index file or a geometry restraint file. An index file contains user-defined list of atoms because sometimes we need to specify a specific group of atoms. I'll show you how you can use index files, but for now, let's concentrate on the necessary input files. Okay, there is something called the GROMACS preprocessor. We summon it with the GROM command. Basically, the GROMACS preprocessor takes all the input files and check and process them. And if everything was fine, it will create a binary input file. It has the TPR extension and is a portable file. And finally, we give the TPR file to the GROMACS simulation engine and it runs the simulation. This flowchart is a bit confusing if you're not familiar with the GROMACS input files, but don't worry, I'll show you the content and usage of all of the input files. Alright, until now we only have a PDB file, so let's create the topology file for this system. And the easiest way to create a topology file is using pdb to GMX command. Actually, this command converts a PDB file to a GRO file, which is native GROMACS format for molecular coordinate, and alongside the GRO file it will create a topology file. The command requires the name of the PDB file with F option and no water, and the name of the GRO file with O option. Let's name it protein.gro. And then the command asks what force field we want to use. For this protein, I'm gonna use AMBER 99SP ILDN. So I'm gonna type 6 and enter. And next we must select a water model. A water model is basically a way to mathematically represent water molecules, and it helps simulate how the water molecules behave and interact with other molecules. And here we have single point charge water models, which are the simplest form of a water model, and a 3-point water model tip 3P, and some more accurate water models. Usually the tip 3P model is a good choice for biomolecular simulations, so I'm gonna choose 1 and enter. Okay, at this point I've got an error, and it says there's a missing atom in the PDB file. Remember, we have downloaded an experimental file from a database, and some of the database files may have some missing atoms. So before we proceed, we must fix the PDB file. There are many tools to fix PDB files, and one of them is H++ from Virginia Tech. The UI of the site is terrible, but it does its job very well. Okay, here all you need to do is click on process structure and choose the PDB file on my desktop, session 2, and the no water file. Okay, and process file. You don't have to change these options, but you can change the pH on 7, but actually it doesn't matter, and the water model on tip 3P. Okay, and process. It takes a while to process the file. Now it's done. I'm gonna click on view results. In this section, key files to download, I'm gonna download the first one. Keep. Now I have the file on the downloads folder, so let's copy it here. Rename it to fix.pdb. Alright, let's use PDB to GMX again. GMX, PDB to GMX, and the output is protein.pdb.gro. Press enter, and 6 tip 3P1. Now I receive another error, but before I solve the problem, I should mention some really important points. First, I should mention that I designed this workshop to have as many errors as possible. That's because a crucial part of using computational programs is resolving errors, and I want to show you as many errors as possible. I could pick a protein that does not have missing atoms and we don't get the error, but this is a crucial part of the workshop. The second point is that always read the output carefully, because I know many students, especially when they get to sequential errors, don't read the second error output, and they say, okay, we did something, but it doesn't resolve the problem. But you should notice that this is a different error from the first one. So you solved the problem, but now you have a new error to resolve, and this time it says there is a hydrogen in the structure that was not found in the force feed files. And if we check the fixed protein with VMD, we can see that the H++ added hydrogen to the protein. So now I want the PDB to GMX command to ignore hydrogens. To do so, I just need to add ignh to the command 6 and 1. Okay, this time everything is fine. And we have a new topology and GRO file. So now let's have a look inside the topology and GRO files. First, I'm gonna open the GRO file because this is less complicated one. A GRO file is similar to a PDB file. Both of them contains molecular structure, but they have different format. The first line in a GRO file is the title, and the second line is the number of atoms. The following lines specify atom types and the geometry. Each line specifies one atom. First we have the residue name, and then the atom type and the number of atom, and finally the geometry of atom. And at the end of the file we have a line that specifies the dimension of the system box. This is a cubic box with A, B and C dimensions. Alright, now let's check the topology file. And as I told you before, a topology file is the representation of the force field for a specific molecular system. It has rather a complex format, which I'll explain it now. Some lines like this one begins with the semicolon. They are comment lines. The program doesn't read them. You can write anything you want in comment lines. And some lines begin with the hash sign like these lines, mainly an include command and some conditional terms. Here the first three lines apply restraint to the system. I'll talk about restraints later on. And this line include the parameters of the water model inside the topology file, which means it tells GROMACS to open this ITP file and reads its content before proceed to the next line. And some lines begin with bracket. They defines directives. Each directive has a specific block of data and must have a specific format. For example, this directive specifies the molecules of the system. In this case, we have one molecule named protein, and it has more complicated directives. Let's move on to the beginning of the file. Alright, here a very important directive is the atoms directive. This directive maps all the atoms of the system and relates them to the atom types of the force field. Let's check what's in each line. Here we have the atom number according to the GRO file, and then the atom type and the residue number and the residue name and atom name and charge group number, charge, and the mass of the atom. Alright, now please pay attention. This line actually says the atom name N from ASN residue in the PDB and GRO file is actually the atom type N3 in the force field. This is very important because only the force field knows how different atoms must interact with each other. So every atom in the structure file must correspond to an atom type in the force field. It has other directives which specify the connection between atoms. There is a bonds directive which specifies the chemical bonds between atoms. Here it says there's a chemical bond between atom 1 and 2 of the system. Here the bond parameters fields are empty, but don't worry, GROMACS can read them from the force field files. And there's a pairs directive which specifies 1-to-4 interactions. A 1-to-4 interaction is an interaction between atoms separated by 3 bonds. Actually, this is a non-bonded interaction. And there's an angles directive specifies the connection between 3 atoms. A dihedrals directive specifies the connection between 4 atoms. I'm not going to explain what's a bond, an angle, and a dihedral because I did it in the first session. And as I told you before, all the parameters fields are empty. That's because this line included the content of the main force field ITP file in this topology file. Alright, a quick note here is that these two files are backup files and GROMACS created them because I executed the pdb to gemx command 3 times. GROMACS does not delete old files, but it renamed them to the backup files. And if you feel you don't need them anymore, you can delete them by this command rm \# Okay, now we have a GRO file and a topology file, and next step is to put the protein in a proper PBC box. First, let's check the GRO file with VMD. We have the same protein and PDB2GMX added hydrogens to it. And if we go into the plugins menu and TK console and type PBC box, it shows us the PBC box, but actually this is not a proper box. So let's close TK console and VMD. I'm gonna edit the box using edit-conf command. We must specify the input GRO file with F option protein.gro and the output file with O option. Let's name it protein in box.gro. A C option because we want to center the protein in the box, and D option specifies the volume of the box. Actually, it specifies the distance between the protein atoms and the walls of the box. We must set the distance so that the water molecules can solvate the protein properly and prevents direct interactions between the protein and its periodic image. Now, if you have a small and rigid protein, you can set the distance 1 nanometer, and if you have a large and flexible protein, you must set it 1.4 and even more, but in most cases 1.2 does the job. And then we must specify the box type. GROMACS supports 4 box type: cubic, triclinic, dodecahedron and octahedron. Dodecahedron is the most efficient one because with the same distance we can have a smaller box. But now I'm gonna use a cubic box because it's easier to visualize. Press enter. The output of the command tells us the dimension of the box in nanometer and the volume of the box in cubic nanometer. The volume of the box is especially important because a larger box requires more water molecules to fill it and making the simulation more expensive. And as I mentioned before, we can reduce volume using a dodecahedron box. Let's have a quick look at the new box using VMD. Now we must fill the box with water molecules, and GROMACS has a specific command for it, GMX solvate. That says the command we must give it the input GRO file with CP and protein in box, and the output GRO file with O option. Let's name it protein in solution.gro. It also needs the topology file because water molecules must be added to it. And another option is CS SPC 2016.gro. SPC 2016 is a GRO file, and the solvate command fills the box with this file, actually with the water molecules of this file. The file is located in the GROMACS main folder and you don't need to find the file. Okay, we have a new GRO file. Let's check it with VMD. Now we have the protein, the blue atoms solvated in a box filled with water molecules. And the topology file. The command made a subtle change in the topology file at the end of the file. Here in the molecules directive, it added a line that specifies the number of solvent molecules. This is a necessary change. Okay, in a biological system, we also have some ions in the solution. You can do it using the GMX gen command. However, this command requires a TPR file for input, and we don't have any TPR file yet. So let's create one. To create a TPR file, we can use the GROMACS preprocessor, but before executing the command, we need to create an MDP file because this is a necessary input for the GROM command. As you can see, we need a GROM file, a topology file, and an MDP file. But we don't need to put anything in the file. Actually, an empty MDP file does the job. So I'm going to create an empty file using the touch command. Let's name it ions.mdp. And now I can use the GROM, GMX, GROM, and it needs the PDB file and the geometry file with the C option. This is the protein in solution. We need this file, protein in solution, and the topology file with P. And finally, the name of the TPR file, let's name it ions.tpr. Okay, I've made a mistake. Let's correct it. Here we need O option. Now we have the TPR file. Now let's use the gen command, gmx. It needs the TPR file with option S and the topology file and the output file. We can name it protein plus ions.grow. So basically the gen command replaces some water molecules with ions, and we can specify the cation and anion with the P name, the name of the cation, Na, which is sodium. We can use potassium as well, and N name, Cl, which is chlorine. And finally, this is crucial to create a neutral system because charged system can cause artifacts. We can do it by the neutral option. Okay, the command asks to select the solvent group because it wants to replace some of the solvent molecules with ions. Here we can select the water group or the sol group. So I'm gonna enter 13 and enter. Okay, now the output says it replaced 9 solute molecules with 9 chlorine ions. And the reason is that the protein has a positive 9 charge and it added 9 chlorine ions to create a neutral system. This is okay. I'm not gonna show you the GRO file again, but let's have a look at the topology file. As you can see now, it includes the chlorine atoms. And next step is minimization. Some of you may ask why we should do a minimization at all. That's because we literally poured some water molecules in a simulation box containing a protein. And many of the water molecules are in the unsuitable positions. They can be too close to the protein atoms and in a higher serine situation. So if we do the simulation now, there's a high chance that the simulation will break. So first we need to relax the system and decrease the strain on the atoms, and we call it a minimization or a optimization because we minimize the energy of the system by optimizing its atoms, optimizing the position of its atoms. Alright, to minimize a system, first we need an MDP file, and I've already had one. So let's check the necessary parameters for minimizing a system. First, if we put a semicolon in a line, GROMACS won't read the rest of the line, like here or here. So the first line is completely a comment line, but this line from here is comment. The first parameter in this file is integrator. However, you can put this one anywhere in the file. The order of parameters does not matter. The integrator specifies the type of calculation. It can be a minimization, an MD simulation, or other type of dynamics. STEP is the steepest descent minimization algorithm. It can also be CG for a conjugate gradient algorithm, or LBFGS for a quasi-Newtonian algorithm, but in most cases the steepest descent does the job. EM step specifies the minimization step, how much atoms can move in a single step. The value is in the nanometer, and steps specify the maximum number of minimization steps. EM toll is the convergence criterion, and if the maximum force becomes less than this number, the minimization will stop. And STList is the frequency to update the neighbor list. I have discussed neighbor list in the first session. Cutoff scheme can be valid or group. In some cases, we are forced to use the group scheme, but in most cases, we should use valid. Coulomb type specify how the program treats the long-range electrostatic interactions. PME is the best method, so if you don't have any reason to use other methods, always use PME. Don't worry about its value, just put it 1. The PME method will increase the value if it's necessary, and RVDW specify the radius of cutoff for van der Waals interactions, and the default method for van der Waals interaction cutoff is plane cutoff. Like this, but you don't have to type the parameter because this is the default value. And plane cutoff means it simply cut the interaction if the value was greater than this number in nanometer. By the way, if you don't know why a cutoff range is necessary, rewatch the session 1. And finally, PBC equals XYZ means it applied the periodic boundary conditions in 3 dimensions. Alright, let's use the MDP file and do the minimization. First, we must create a TPR file using the GROM command and the name of the MDP file, and we need the topology file. For the GRO file, be careful to choose the last one, which is protein plus ions. And finally, the name of the output TPR file, min.tpr. Okay, it does the job and we've got no errors, so now we can minimize the system using GROMACS MDP and vdefnm and the name of the TPR file. Here v option means I want more information in the output, and defnm means I want the program to create all the output files based on this name. The name must be same as the TPR file. Please pay attention, I didn't write min.tpr, just the prefix of the name, and it will create all the output files with the min prefix. Alright, I'm gonna press enter. The output says the minimization converged in this step, which is fine because if it didn't, we have a problem. In most cases, we can solve the problem by changing the minimization algorithm to CG. In this case, we don't need to, everything is fine. And it has created some output files. I will explain them later on, but for now, let's proceed to the next step. And next step is the equilibration. Although we've already optimized the system, but that's not enough. Remember, this is an artificial system and the arrangement of the water molecules may be very different from what we have in a real solution. So before any product simulation, we must equilibrate the system. And the whole point of equilibration is that we must gradually change the system's variable until it reaches some stable state, because if we release all degrees of freedom at the start, the simulation will collapse. For that reason, in the equilibration step, we always impose some sort of restraint on the system. I'm gonna tell you what's the meaning of restraint, but for now, let's have a look at the equilibration parameters. Okay, here I have nvt.mdp. I must mention that all sessions have a file section in which I put all the MDP files alongside other necessary files. So don't bother yourself with writing parameters or taking images of them. Alright, here the equilibration process takes place in the NVT ensemble. That's not strictly required to start equilibration in the NVT ensemble. However, except for some certain molecular systems like solid state systems, it's a really good practice to start in NVT, because in the NVT ensemble the program only changes the temperature, but in the NPT it also changes the volume of the simulation box. And as I mentioned before, we must gradually change the system. Here, the first line is a position restraint parameter. Actually, this restraint has been created automatically by the pdb2gmx command. And this parameter here actually is a trigger to turn on the restraint. The main body of the restraint is in the topology file. Alright, here. This section states that if pose is defined in the MDP file, like this line, if pose is defined in the MDP file, then the pose.itp file must be included in the topology file. And finally, end if. So it only works in the MDP file when there is a conditional term in the topology file for it. So let's see what's inside the file. Pose file is a very simple topology file. It only has one directive. This directive contains atom number, type, one is harmonic restraint, and then fx, fy, and fz. And these three ones are force constants in kilojoule per mole per cubic nanometer. So this line means if atom 1 wants to move in x, y, or z direction, a harmonic restraint with the 1000 kilojoule per mole force keep it in its place. And this file lists all the heavy atoms of the protein. Please note that we don't fix or freeze atoms in the coordinates, we only put restraint on them. This is like fixing atoms by connecting them to some elastic bands. Another point is that you can define and use other restraint in a topology file like this one, and then use them and turn them on in the MDP file. But for now, we only need a restraint to keep the heavy atoms of the protein fixed. Okay, let's come back to the MDP file. So first we have a restraint and then run parameters. The integrator is the most important parameter of the file, and it indicates the type of calculation. MD means molecular dynamic, and actually it is a leapfrog integration method. We will use MD for any MD calculations in the NVT or NPT ensembles. N steps is the number of steps, how many steps we want to continue the simulation. DAT is the duration of a single step, the unit is picosecond. Please note that we can determine the overall time of simulation by multiplying these two numbers in picosecond. Next, the output control parameters. NSTXOut specify the frequency by which GROMACS will save the coordinates of atoms in a trajectory file. 500 means it saves them every 500 steps. Similarly, we have another parameter, NSTVout, for saving atoms' velocities in the trajectory file. NST energy specified the frequency of saving energies in the EDR file, and NST log specified the frequency of saving data in the log file. Don't worry, I'll show you all the output files, but for now let's check the bond parameters. Here we have constraint, and please don't confuse constraint with the restraint. They are completely two different things. I've explained restraints, so let's see what's a constraint. A constraint enforces bonds or angles to be fixed in a simulation. By applying constraints, we reduce the degree of freedom of the system and increase the efficiency of the simulation. I can constrain all bonds of the system, but this is not how a natural system works. But a very clever choice for constraints is H-bonds. That's because hydrogens move very fast. The frequency of H-bonds vibration is very high. So if we don't fix H-bonds, we must use a smaller step time, DT, and it has a huge impact on the simulation time. Just imagine if I change DT to 1 femtosecond, then I must double the number of steps to get the same simulation time. And fortunately, H-bonds vibrations are not biologically relevant, so we can safely apply a constraint on them, and also we can set the constraint algorithm. Links is a stable and efficient method, so if you don't have any specific reason, just use links. And then we have non-bounded settings, and I've already explained most of them on the previous MDP file. This one is new, and basically it applies long range dispersion correction on the van der Waals interactions, which means we will have more accurate van der Waals interactions. The value of the parameter can be no, NR, and NR per S. NR per S means it applies correction on energy and pressure. And because we want to simulate on the NVT ensemble, we must have a way to control temperature. Actually, we must apply a thermostat, and we can set it using the T-couple parameter. The V-rescale thermostat is a great choice, and you can use it for both equilibrium and product simulations. Next parameter is temperature coupling groups. Using this option, you can define separate thermostats to be coupled with different parts of the system. The reason is that if a single thermostat is applied to the entire system, energy may transfer unevenly between different molecular components, and it will create an artifact called hot solvent cold solute, because if we use a single thermostat, the solvent molecules absorb more kinetic energy. So we should define two thermostat group, one for protein and one for solvent molecules. Next parameter is coupling time constant, and it defines how often the temperature will be adjusted with the thermostat, and we must set one constant for each group in picosecond. For the various scale thermostat, 0.1 to 0.5 is okay, and the reference temperature for each group is 300 Kelvin. And finally, the velocity generation. Velocity generation means GROMACS will generate velocity of all atoms at the beginning of the simulation according to the Maxwell distribution, and it will put this temperature in the Maxwell equation. Alright, let's create the TPR file using the GROMACS command. nvt.mdp and p topol.top and C. Now please pay attention. For the coordinate file, we must give it the last GRO file from the minimization, which is this, and O nvt.tpr. Okay, we've got an error, and it says because we use the restraint in the MDP file, we must give it a restraint coordinate file. The solution is easy. We can give it the same coordinate file using our option. Alright, that's done, and now we have a new TPR file, nvt.tpr. So let's run it using mdrun. nvt. And now we have some new files which are I'm gonna show you the output files later on, but for now I want to do a simple analysis and check how the system temperature changed during the simulation. To do so, I'm gonna use GMX energy and the name of the EDR file, nvt.edr. The EDR file is an output file which contains the energy data of the simulation, and the name of the output file, let's name it .xvg. And here it asks which term I want to have, and I'm gonna choose temperature 16. And press enter again, and it says the average temperature of the simulation is practically 300 Kelvin. So now we can claim that the system has reached the desired temperature. And also we have an XVG output, this one. And actually this is a diagram file, you can check it using Grace, Grace. However, if you don't have Grace on your system, you can easily install it using sudo apt install Grace, just Grace, not xmgrace. I've already installed one, and I can open the file. Here I'm gonna type xmgrace and the name of the file. The diagram shows that the system reached the desired temperature very fast and then fluctuate around it. This is completely okay if the temperature goes up and down. This is a stable state, not a static state. Okay, next step is an MPT equilibration, because now we want to adjust the pressure of the system. Okay, first let's have a look at the parameters file. Most of the parameters are the same as those in the NVT file, so I'm not going to explain them again. But in the NPT file, we need to define a barostat. I've already talked about barostats and thermostats in the first session, so now we just check the parameters. P-couple type is series scale. This is a proper barostat for both equilibrium and product simulations. Time constant of coupling is 2 picosecond. Every 2 picosecond it does the job. The reference pressure is 1 bar, and the compressibility of the system is equal to the compressibility of water. And for a restraint MPT simulation, we need another parameter, coordinate scaling. COM stands for center of mass, and basically coordinate scaling adjusts the original positions of restraint atoms when the simulation box changes. If we don't use it for a restraint NPT calculation, the restraint atoms may drift during the simulation and cause artificially large forces and instability in the system. Alright, let's create the TPR file, GMX gromp, and the parameter file, npt.mdp, and topology, and the coordinate file. We must use the last GRO file from the NVT simulation, nvt.gro. And I'm going to use the same file as a restraint file, nvt.gro, and finally the output file, npt.tpr. Okay, this is totally fine. We can run the simulation. npt. Okay, the simulation is done. And now I can check the pressure of the system using GMX energy. I must give it the EDR file npt.edr and the output file, let's name it pressure.xvg. And here I'm gonna choose total pressure number 18 and press enter. Alright, the average pressure is not close to 1 bar, but this is not wrong because pressure is a quantity that fluctuates widely over the course of a simulation. And also we can check the XVG file by xmgrace pressure.xvg. The diagram shows that the pressure widely fluctuates during simulation, and actually it's quite hard to judge the equilibrium according to the pressure. So instead I'm gonna check the variation of the system volume during the simulation. To do so, I'm gonna use the GMX energy again, but this time volume.xvg. Okay, and here I'm gonna choose volume 23 and press enter twice. Let's check the volume diagram. Grace volume. The diagram shows that the volume decreased very fast at the beginning of the simulation, and then it has a stable state with a little bit fluctuation. Alright, the system is now ready for the main simulation, but before that I recommend always check the system structure by your eyes. npt.grow. This is the last grow file. Okay, everything is fine. So now let's move on to the main MD simulation. Okay, I have an MDP file for the MD simulation. Actually, the MD simulation also is in the NPT ensemble. So what's the difference between the main MD simulation and the Equilibration NPT simulation? And the student can tell the difference now. Okay, I'll give you 5 seconds. The main difference is that in the product simulation, we removed the restraint on the protein molecule, and now the protein atoms can move freely, so this is the real simulation. And also we have some subtle changes. Here, NSTX out compressed create a compressed trajectory file. The compressed trajectory file has XTC extension. The uncompressed trajectory has TRR extension. The main difference is that compressed trajectory only saves coordinates, but uncompressed trajectory also saves velocities and forces. And the point is that in many cases only coordinates are enough and we don't need velocities and forces. And we can prevent a bulky TRR file by setting these numbers to 0. This one and this one. Now it won't create a TRR file but only an XTC file. Don't worry about velocities and forces. If you need them later, you can quickly recreate a TRR file from an XTC file by rerunning the simulation. So if you have a long and large simulation, you can safely exclude the TRR file. The other difference is that barostat in this file is Rahman. This is the best one for product simulation, and the product simulation doesn't need the coordinate scaling because it doesn't have any restraint. Okay, let's check it with the gromp command. GMX gromp. It doesn't need a coordinate file for restraint because it doesn't have any restraint. So the output file. Alright, everything is fine. So I'm gonna run the simulation. Okay, it takes a while, so I'll be right back after the simulation has finished. Alright, the simulation has finished, so let's have a look at the output files. First thing first, I should mention that some of the output files like the log file or the GRO file are simple text file, and we can open them using a text editor like vi md.gro, and we can see the content of the file, or md.log. Other output files like xtc, edr, or the cpt file are data file, and we can't see the content of them using a text editor. If we open one of them, this is what we get, and only GROMACS can read the data. Okay, the CPT file, the MD-CPT file, is the GROMACS simulation checkpoint file. GROMACS makes this file during simulation and updates it every 15 minutes. And we can use this file to restart or extend a simulation. Let's say we had the simulation and it interrupted for any reason like power failure or job timeout on a server, and for a long simulation this is very painful to start the simulation from the beginning, so you should know how to restart a simulation using the checkpoint file. I'm gonna create a new folder and copy the TPR file on it. Now to show the simulation process, I'm gonna run a simulation and interrupt it before it finishes. Okay, I've cancelled the simulation using Ctrl+C. Now to restart the job, I just need to add the CPI option to the command, CPI, and the name of the CPT file without the extension. Okay. Alright, now you can see that the simulation restarted from this step. This one from this step. Let's say you did a simulation, but after finishing the job, you realized that you need to continue it for a longer time. In this case, you can extend the simulation time using convert TPR, and you should give it the previous TPR file with this option, md.tpr, and the output TPR file, the new TPR file, let's name it md.x.tpr, and how much you want to extend the simulation time in picosecond. So this command extends the simulation time by 1 nanosecond. In the output you can check the original simulation time and the new simulation time. To run the extended simulation time, GMX MD run, and we give it the name of the new TPR file, MD with option S, and the CPT file, CPI md.cpt, and the nm. Alright, here we must give it the prefix of the original simulation files, MD, and press enter. Alright, as you can see, the simulation continues from this step. Alright, there are some other output files There's an EDR file. This file is the energy file and contains thermodynamic and statistical data like temperature, pressure. We can use it using the GMX energy command. And we have a GRO file. This file is the last coordinate of the simulation. We have a log file. The log file contains timing data and energy components. You can open it using VI. This section at the end of the file shows the average energy components of the simulation and a trajectory file. This file can be a compressed XTC file or a TRR file or both of them, depend on what you have requested in the MDP file. And actually the trajectory file is the most important output file. GROMACS saves the system's coordinates every step in the trajectory file. You can change the frequency of saving in the MDP file as I told you before. We can check the trajectory file using VMD, but it's a little bit tricky. Let me show you how. First, we need to center the protein in the simulation box using GMX trajconv. We must give it the TPR file and the XTC file. XTC file with option F and the output trajectory file. Let's name it md fix.xtc. To center the structure, I'm gonna add center, and to fix PBC issues, PBC mol. Then it asks which group I want to be in the center, and I'm gonna choose protein 1. Then it asks which group I want to be in the output file. I'm gonna select system because I want all of the system in the output trajectory file. Now we have a new trajectory file, this file. To visualize the trajectory file, first I'm gonna open it with VMD. Then I'm gonna select the trajectory from here and file, load data into molecule, and here I'm gonna find the final GRO file, md.gro, okay, and load. Now you can see the system variation by clicking on play. Let me bring the PBC box. And remove the water molecules. You can see that the protein is in the center of the box during simulation. Alright, we successfully completed the first MD simulation, so let's do some basic analysis. The first analysis is RMSD, root mean square deviation. This analysis calculates root mean square difference in atomic positions relative to a reference structure. In simple terms, RMSD measures a structural deviation relative to a reference structure, and we use RMSD to check overall structural stability and deviation. A low RMSD means that the structure remains stable during simulation, and a high RMSD may indicate unfolding, conformational changes, or instability. The other analysis is radius of gyration, and this is mass-weighted average distance of atoms from the center of mass. And basically, the radius of gyration measures a structural compactness during simulation. So we can use it to monitor compactness, folding and unfolding of proteins. Low radius of gyration indicates a compact and folded structure, and high values indicate a more extended or unfolded state. Alright, let me show you how we can perform these analyses. I'm going to begin with RMSD. To do a RMSD, first we need a centered and PBC fixed trajectory. And we already had one. This one is the fixed trajectory. The RMSD command is GMX RMS, and the name of the TPR file md.tpr, and the name of the trajectory and the name of the output file. Let's name it RMSD.xvg. This is a diagram file, and it's better to change the time unit to nanosecond instead of picosecond, and press enter. Now we should select which group must be used for the least squares fit. We can select the whole protein, but if we do so, the fluctuation of the diagram will be high because of the protein side chains. So the best choice is the protein backbone, number 4. Again, I'm gonna select 4 backbone. Now we can check the result by xmgrace and RMSD.xvg. The result shows that it has a slight increase in RMSD and then a very low fluctuation here. So we can state that we have a stable protein without any significant structural changes. Please note that this is a tutorial simulation and we only simulate for 1 nanosecond, and a real simulation must have a much longer simulation time, like 50 nanosecond or 100 nanosecond or more. The other point is that in the command, this TPR file is the reference structure, and you can give it other structure like differs, minimize structure. But if you want to analyze the simulation deviation, this one is the best choice because this is the immediate structure before simulation. Alright, let's move on to the radius of gyration analysis, and we can do it using this command gmx gyrate and md.tpr and f md fix.xtc and org.xvg. Okay, here I'm gonna choose protein. For radius of gyration, always choose the whole protein, 1, and it's done. Now let's check the result. xmgrace rg. Okay, as I just told you, the radius of gyration is actually the average distance of atoms from the center of mass. So a low value of it indicates a compact protein, and as you can see, it fluctuates around 1.46 nanometer, and this is a low value even for a small protein. So we can say that this is a compact protein. The amount of fluctuation is around 0.04, which means the protein maintains its compactness. Another important thing for interpreting a radius of gyration plot is the slope of its baseline. And if the slope is increasing, it indicates that the compactness of the protein decreases and it probably undergoes an unfolding process. And if the slope is decreasing, it indicates that the protein's compactness increases and it probably undergoes a folding process. But here the slope of the baseline doesn't change, so we don't have any folding or unfolding process. Alright, we did 2 basic analyses. In the upcoming sessions, we'll do more complex analyses.